Here we go. Our very 13th episode, Miss Phoenix.
Yay!
We're doing it.
Almost
that means
to
we
15.
have been doing this for 13 weeks.
13 Sundays.
Yeah, that's 3 months, bro. Can you believe it? Isn't that crazy? 3 months.
Just a week over 3 months, because it's currently June 1st.
Right, so we've already done the 3 months. Now we're working on the next.
It's June 1st. I'm recording.
As I'm recording. Yep. I'm pretty sure in the last episode we forgot to tell people where we were. What? No. How to find us.
It's okay.
Linktree.com/BOTQS.
I know, but there's so many other episodes that we do say.
Yeah, we did. All right. You're Phoenix, I'm Will, and we're here to bring on the questions. And we already said about finding us on linktree.com/BOTQS. Links to listen, links to watch. Watch on YouTube.
Yes.
So, Miss Phoenix, what question are we bringing in this episode?
How much does the Earth weigh? And how do we know that?
Right. So, thinking about this, when we first decided we would do this question, I was like, so what? Scientists who just estimated, there's a bunch of dirt. So how much does this much dirt weigh? And we will estimate how much is there. We'll get the radius of the Earth and blah, blah, blah. How much does this type of rock weigh, and how much does this much water weigh, salt water, fresh water, and then just give a crazy estimate.
But not all dirt and water and rocks, because there's the core, the inner core and the outer core, the mantle.
Yeah.
All that magma.
I'm not entirely sure how well that stuff's factored in. There's an assumption, I think it's just incredible assumptions on, we can't get to the core, can't exactly put the whole freaking planet on a scale.
Yeah. There's no space scales yet.
Who knows?
And that part wasn't scripted. We just did that.
All right. We'll get into the notes here and just figure this out. Maybe. It's a lot of info. When inquiring about the heaviness, quote, heaviness of Earth, it is crucial to first establish a precise scientific distinction between mass and weight. While often used interchangeably in layman's terms, these two concepts represent fundamentally different physical quantities. Mass is an intrinsic property of an object, quantifying the amount of matter it contains. Solid, liquid, gas. And they have decided that there is a fourth state of matter they decided is plasma. So, like the energy of the sun, the energy of fire coming off.
Or like ghosts.
Ghosts?
They're kind of made of cyto. What kind of plasm is it?
Ectoplasm?
Yeah, ectoplasm. So it's a type of plasma.
Plasm? Not plasma, plasm.
I think it's the same thing. Because ghosts are just made of like spirits and ghosts are just made of like energy.
I just read an article about
have energy.
a fifth state of matter.
A fifth?
The Bose-Einstein condensate, or condensate, BEC. BECs are created when a gas of bosons is cooled to temperatures near absolute zero, causing them to behave like a single superatom.
And it's BEC.
BEC? What'd I say? BC?
It sounded like BC because you said BEC so fast. So I'm just clarifying that it's not BC, as in before Christ if you're Christian, or like BCE before current era.
Nice. Well done.
I know my facts, okay? But it's BEC, not BCE.
Right. Bose-Einstein condensate.
I don't know what that means.
Bosons are particles that obey Bose-Einstein statistics, meaning they can occupy the same quantum state. Cooling to near absolute zero. When a gas of bosons is cooled to extremely low temperatures, a significant fraction of them will occupy this lowest possible energy state, single superatom. At these temperatures, the bosons begin to behave as a single macroscopic quantum object, like a superatom, with properties that are not seen in ordinary matter. So it's a super state of matter, but let's just stick with the ones we know. Solid, liquid, gas.
I didn't understand much of what you said.
I didn't either. I just read the words.
You know what? I do that too.
I said mass is an intrinsic property of an object, quantifying the amount of matter it contains. We clarified that. It is measured in kilograms, grams, pounds, ounces, etc. It remains constant regardless of an object's location in the universe. So your mass here is the same amount of mass, all the stuff that makes up Phoenix is the same thing that would be on Saturn or Jupiter or Pluto or
the moon.
I was going to go way further out than that. Alpha Centauri. How about
Uranus?
That? No. Uranus too. All right, grab the next one. Conversely.
Conversely, weight is the force exerted on an object due to gravity, measured in newtons. An object's weight is dependent on both its mass and the gravitational field strength of the celestial body it occupies. Consequently, an object's weight can change significantly depending on its location. For instance, an object would weigh considerably less on the moon than on Earth due to the moon's weaker gravitational pull.
Aha, there you go. Weight can change. Yes. So,
mass cannot change, weight can change drastically.
Neil deGrasse Tyson has said that if you want to lose weight, go to space. You'll weigh a lot less.
Yeah.
But if you want to lose mass, you're going to have to put the work in. Given this distinction, when scientists refer to the heaviness of Earth, they are invariably discussing its mass, not its weight. The concept of Earth weighing something is scientifically meaningless, as weight inherently implies a gravitational interaction with another body. So it doesn't really, I don't think it would even jive if you think of the gravitational pull of the sun on the Earth. I don't think it would even work because we're in orbit. So let's not even think about that. So our weight is measured by the celestial body that we're on. We got that, right?
Yeah.
The current best estimate for the mass of Earth, a cornerstone value in planetary science, is M, and this symbol is a circle with a plus in it. M, circle plus. I don't know. That means
tiny circle.
Yeah.
Like that R symbol on like toys and stuff.
So that means mass of the Earth. That's what that symbol stands for. The M, circle with plus in it. Mass of the Earth equals. Here we go. This is going to be fun. 5.9722 times 10 to the 24th kilogram, with a relative uncertainty of 10 to the negative fourth. So it could fluctuate with 4 zeros, I guess. This colossal figure is equivalent to an average density of 5,515 kilograms per meter cubed, and using the nearest metric prefix can be approximated as 6 ronnagrams. What the heck is a ronnagram, Phoenix?
I have no clue.
So I put a little link there. So we can go to here. So a ronnagram is a bunch of kilograms. So 1 kilogram is 1,000 grams. So we got 1 gram. 10 grams is a decagram. 100 grams is a hectogram. 1,000 grams is a kilogram. And then 1,000,000 grams is a megagram.
A milligram.
Mega. Megagrams every year is essentially a ton. 3 more zeros, gigagram. 3 more zeros, teragram. We'll get into all this stuff here in a second. It goes from gigagram, teragram, petagram, exagram, zetagram, yottagram, then finally to the ronnagram, which is 1 followed by 24 zeros, 1 septillion. Right? Is that the septillion one? I think so. Grams.
We had a 27, not a 24.
What did? For the ronnagram? Oh, okay. Yeah. So that's the next one up. So that would be 1 octillion grams is 1 ronnagram. 1 septillion kilograms is 1 ronnagram. That was ridiculous, right? 1 ronnagram is 1 septillion kilogram. That's followed by 24 zeros. Quick note on names of mega numbers because I was curious too. Here goes. 1,000, 3 zeros. Million, 6 zeros. Billion, 9 zeros. Trillion, 12 zeros. Quadrillion is 15 zeros. Quintillion is 18 zeros. Sextillion is 21 zeros. And septillion is 24 zeros. And then now we get into like the Spanish version of the numbers. So it goes from septillion to octillion to nonillion to decillion? Or yeah, I think it's decillion.
Would it be decadillion?
Decadillion.
Crocodilian.
I don't think you're supposed to say that. Decillion.
Crocodilly-doo.
It just seems like outrageous numbers. Just totally outrageous numbers. That's why they started giving them these, just the names instead of so many zeros.
Yeah.
And when you see numbers laid out such as 5.9722 times 10 to the 24 kilogram, it actually means adding 24 zeros after the decimal, after the numbers that are already after the decimal. So in this case, there's 4 numbers after the decimal, so we'll get 20 zeros after the last number after the decimal.
That's too many.
So this would be 59722 and then 20 zeros. That would actually be 5 septillion, 972 sextillion, 200 quintillion kilograms. Let's round that up. 6 septillion kilograms, or 6 ronnagrams.
Oh.
Give or take a megagram or 2. That's how much the Earth, quote unquote, weighs. That's the mass of the Earth. 6 septillion kilograms.
That's so many.
That's still just a massive estimate. We can't directly place Earth on a colossal scale. That's, of course, physically impossible. Right. Therefore, the planet's mass must be determined through intricate, indirect methods, relying on fundamental laws of physics and meticulous measurements rather than any form of direct weighing. Huge estimate. Somebody wanted to know.
Somebody was curious.
And they did the work for the math.
Yeah, they were curious enough to do all that work.
And I wonder if in the time they were like, man, there's just not enough numbers. We got to make up some bigger numbers for this kind of thing.
How did they come up with numbers at all?
I don't know.
Why would anyone come up with numbers at all?
Somebody come up with the ridiculous amount of numbers. The petagrams and the megagrams.
Founder of school. I don't like them.
Yes, you do.
They're probably ancient Mesopotamian because Pretty sure they had school back then too. Like what?
Yeah,
would go to school?
maybe that's a good question to ask. Like, who came up with the idea of a structured daily, near daily school form that we know today?
Wait, yeah.
It's a Monday through Friday, generally 180 days in a given school year before you can move on to the next level.
Like people, like people in ancient Mesopotamia would go to school to become scribes, but how was school even created?
Very good question. When you're working on summer vacation, do you really want to talk about school during summer vacation?
Oh, definitely not.
We'll talk about Mandela effects and Rasputin later on. For now, we should continue on figuring out how we know the Earth weighs 6 septillion kilograms. Go ahead. Read the theoretical bedrock, blah, blah, blah.
That's still? Or
no, the theoretical.
The theoretical bedrock for calculating Earth's mass lies in Isaac Newton's law of universal gravitation. This law posits that every particle in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Scientists leverage this principle by using the known radius of Earth and the gravitational force exerted on an object at its surface to infer the planet's total mass.
To apply this formula, 3 critical pieces of information are required. The acceleration due to gravity, lowercase g, at Earth's surface, which can be measured by observing how fast objects fall. Earth's radius, capital R, determinable through geodetic measurements, and the universal gravitational constant, capital G. Of these, the gravitational constant, capital G, proved to be the most elusive and challenging variable to measure accurately, its precise determination being a pivotal step in quantifying Earth's mass.
The first successful measurement of the gravitational constant, a monumental achievement, often
colloquially.
Yeah,
so it's why don't we just look it up?
Yeah, I'd rather look it up.
Colloquially, in the language of ordinary familiar conversation, the storms hit several states along a corridor colloquially referred to as Tornado Alley. So it's in the language of ordinary or familiar conversation, informally. So it's like a
informal way of speaking.
Yeah, sort of. So, but more like regionalized. So, what are examples? So, Pennsylvania, yep, there you go, exactly, perfect.
Jimmy's instead of sprinkles.
In New Jersey.
Or
pop instead of soda in the Midwest.
Or
colloquially.
Some people in Australia, I'm pretty sure, call it Coke.
It's all Coke. And Pappy called it soft drink.
Yeah. I don't know where we got soft drink from.
That's just how I grew up.
Where's the hard drinks?
Those are adult sodas.
Ah, so soft drinks are for kids.
That's right. There you go. Figured it out.
There, you answered my question.
Yep.
Question number 1 brought. And answered.
There you go. Done. Where were we? You were reading about the first...
Colloquially.
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 Man, now you messed me up.
Colloquially.
There you go. Referred to as
referred to as weighing the Earth, was conducted by Henry Cavendish in 1798.
Mm-hmm.
That was a long, long time ago.
Yep, a couple hundred of them.
About 300 years ago. A little less than 300, but just about.
227.
What?
227. This is 2025. 2025.
A little less than 300 years ago would be 1798.
227, come on, read it!
Cavendish employed a device known as a torsion balance. This ingenious apparatus consisted of two small lead spheres, suspended from a wire with two much larger lead spheres positioned nearby. The tiny gravitational attraction between the large and small spheres caused a measurable twist in the wire, allowing Cavendish to quantify the gravitational force between known masses. This groundbreaking experiment enabled him to calculate the value of the gravitational constant, uppercase G.
Yeah, so he hung two small spheres of lead and he hung two large spheres of lead. And there was enough of a difference in the string that held the small spheres that he could measure it, and there was a gravitational force pulling in the small spheres to the large spheres that's measurable. So then he could calculate that on grander scales, celestial body scales, like the moon or the Earth.
Other planets, the sun, other stars.
Right, but you have to assume, you have to figure out the radius of these monumental things. From his measurement of G, the gravitational constant, capital G, Cavendish was able to calculate Earth's average density. He determined Earth's density to be 5.448 times that of water, a value remarkably close to the currently accepted figure of 5.514 grams per centimeter cubed. By combining this derived density with Earth's known volume, calculated from its radius, Cavendish could then estimate the planet's total mass. This experiment was not merely a technical measurement, it was a pivotal moment in scientific history. It transformed the understanding of gravity from a purely theoretical concept into a quantifiable force acting between everyday objects, providing the empirical link necessary to apply Newton's law to a celestial body like Earth and determine its intrinsic matter content for the first time.
Building upon Cavendish's foundational work, modern scientific techniques have continuously refined the values of acceleration due to gravity, Earth's radius, and particularly the gravitational constant. Advanced instrumentation in satellite measurements have led to increasingly precise estimates of Earth's mass. However, despite these improvements, some uncertainty in the precise value of the gravitational constant still persists. This inherent uncertainty propagates to the overall precision of Earth's mass estimate. Nevertheless, scientists have converged on the current best estimate of Earth's mass as approximately 5.9722 times 10 to the 24th power kilograms, or 6 ronnagrams, like we just talked about.
Just lisp your way through it. The measurement of Earth's mass stands as a testament to the iterative and cumulative nature of scientific progress. Foundational theories such as Newton's law of universal gravitation are rigorously validated and refined through ingenious experimental designs, like Cavendish's torsion balance. Ingenious, what am I talking about? refined through ingenious experimental design like Cavendish's torsion imbalance. Subsequent technological advancements then allow for continuous improvements in precision and accuracy. This ongoing process exemplifies how scientific knowledge is built upon previous discoveries, with each step adding depth and precision to our understanding of the cosmos.
A common question arises regarding whether the Earth is gaining mass due to the increasing human population and the proliferation of man-made objects. Scientifically, the answer is unequivocal. Human activities, including population growth and construction, do not add mass to the Earth.
Right. That is we'll get into it in the next one, but the law of conservation of mass. Also, the law of conservation of, well, I guess that's what it is. But energy cannot be created nor destroyed. It can only change forms. So we'll see all these buildings going up, and we see all these things being made. And there's always new cars on the road, and there's constantly new things. There's new people. There's 8 billion people on the Earth. But it's all contained in Earth. So that means everything that's being made is pulling from the greater parts of the Earth. We're just recreating parts of the Earth for human activities.
Yeah.
Which is crazy.
And that's why when people are ghosts or spirits, their energy is still here. It's just in a lower frequency or lower frequency, so that and ours are in higher frequencies.
How deep do you want to go on this?
I don't know. I just want people ghost hunt, and I know that.
I know. So my question is, where does that ghost energy come from? Because there's constantly new people. There's not less people. There's always more new people. Yes, people are dying from various things all over the world, but there are more people coming onto the Earth, new life on the Earth, than there are people leaving, the consciousness leaving the Earth. Where does all the consciousness come from?
Oh no. That's
an existential crisis thing.
I just know that spirits and sometimes demons that are summoned and can come to Earth have very much lower frequencies, and if you have a lower frequency in your body and self, then spirits or like demons and all that can attach to you. You don't want that to happen.
No, we don't mess with that. No,
so
no.
We want a high frequency, not a low frequency. High energy, no low energy.
Crazy to think about that. So the lower frequency, is it coming from a different plane of existence? I know we are way off topic, but the idea of the law of conservation of matter, of mass, of energy, it can't be destroyed nor created from nothing. It's just transformed, but where are all the energies, the ghost energies? How are they even possible? And something that just came to my mind, it wouldn't be, what is the youngest ghost? Well, I guess it would be, what's the newest ghost? Because we always talk about ghosts from like Civil War and Gettysburg. That was working on 200 years ago.
Yeah.
Not quite. But 1865-ish, around that time. We're not at 200 yet. 160 some. Anyway, despite the math, those ghosts are lurking out there, Gettysburg or other Civil War sites. Are they the newest ghosts? Who are the newest ghosts? There was a lot of slave stuff, but I guess around the Civil Wars when that stuff ended. But what about like voodoo stuff or the Winchester lady? She was terrified of her ghosts, and that I'm pretty sure that was the early 1900s. The Winchester Mystery House. We'll get into that too. That's fun. But the newest ghost, like, do we have new ghosts from, say, 9/11? That was 20, almost a quarter century ago. Almost 25, 24? Yeah, at this point, 24 years ago. Almost 24 years ago, as of this recording. Are there ghosts from that? Because that was a huge emotional event.
There probably is, because sometimes, well, one thing that why ghosts are here is that they don't know how to pass on, and there's something like that they need to get rid of or like figure out to pass on.
Is it that simple?
Or they need help passing on.
Is it that simple? They just need to tell somebody their story?
Sometimes. But sometimes there's a different, like, more evil spirit keeping them here.
What does that spirit want? Just to be a jerk?
Probably to keep the other ghosts there to, like, because it's usually a lot of men.
Yeah.
To other women, younger women.
And some heavy true crime stuff you might be working on. We'll get into true crime at some point, I think.
We definitely will.
It's dark. We got a lot of science stuff that we can get into. Speaking of, we should continue with this one. The law of conservation of mass. This conclusion, so the conclusion that you said about scientifically the answer is unequivocal. Human activities, including population growth and construction, do not add mass to the Earth. This conclusion is rooted in a fundamental scientific principle, the law of conservation of mass or matter. This law states that within any closed system, matter cannot be created or destroyed. It can only be rearranged or transformed from one form to another. The Earth is a closed system. This means that the total mass of substances before and after a physical or chemical change remains constant. When applied to biological growth, such as humans, animals, or plants increasing in size, the principle clarifies that no new matter is being introduced to the planet. Organisms grow by incorporating existing matter from Earth's environment, drawing water and nutrients from the soil and carbon dioxide from the atmosphere. This process is merely a rearrangement of atoms and molecules already part of the Earth's system, not an addition of new mass. For example, if 10 grams of sugar are added to 200 grams of water, the resulting solution will have a total mass of 210 grams. Similarly, ice melting into liquid water retains the same mass because no atoms are created nor destroyed.
They are just changed.
Right. The Earth is a closed system.
It kind of reminds me about, like, food webs and food chains, because we just learned that in science.
The circle of life.
Sure. But it starts out with producers, which get energy from sun and water, and primary consumers don't take all of the energy, but only take enough. So there's still some energy in the producer, but it will lower as you go up to a tertiary consumer or more. And then the whatever, food web or chain, the tertiary will always go back to decomposers, which, like mushrooms, like, will fertilize more soil so that more producers make more energy, and it keeps on going.
Perfect example of the transfer of energy. The whole food chain, life cycle, all that.
Yeah.
That's a perfect example. It's a closed system.
Yeah. Like, I recently did a project, kind of, on the Everglades for science, because that's the national park I chose, and I made a food chain, and I started out with wildflowers as my producer. I did mice slash rats as my primary, then a raccoon for my secondary, then my tertiary was an alligator, and then my decomposer was a mushroom. And it went right back to the wildflowers.
Perfect. And then at that time, you probably weren't thinking, well, it's just a transfer of energy.
Not really. I mean, we did kind of learn about that in like fourth, fifth. Like, it's all just energy. It'll just decrease from each animal. Because other animals will keep energy in their own.
Right. They get it from multiple sources.
Mm-hmm. And that's basically what food webs are. It's just multiple sources going to one.
That's awesome. The whole thing is awesome.
Or one animal going to multiple sources, multiple other animals.
And it's all transfer of energy. So we're talking about the law of the conservation of mass.
Yep.
That is the basic. That's basically how it works.
Yeah. No energy is always. Energy never leaves. It just moves.
Right.
Changes.
Where does your consciousness go? Deeper. That's not in this episode.
No. We need to get back on track.
Yep, go ahead. Same principle applies.
The same principle applies to man-made objects. Buildings, vehicles, and all other artificial structures are constructed from materials extracted from Earth's crust, atmosphere, or oceans. Whether it's steel from iron ore, concrete from limestone, and clay or plastics from petroleum, these materials are simply transformed and rearranged from matter that already exists on the planet. Even rockets and satellites launched into Earth's orbit are composed of Earth-derived materials, and the vast majority of these objects eventually deorbit and fall back to Earth, resulting in no net change to the planet's overall mass.
Awesome. For the purpose of understanding the impact of internal biological and anthropogenic, an adjective that describes changes in nature made by people. If your town has rerouted water from the river for drinking water, that is an anthropogenic activity. The planet can be effectively considered a closed system in terms of matter. This perspective is crucial because it highlights that within Earth's boundaries, matter cycles and transforms, but its total quantity remains conserved. This will contrast sharply with things we are about to discuss, which do involve the exchange of matter with outer space and thus can subtly alter Earth's total mass. Subtly.
It also kind of reminds me of the water cycle. Like, water never leaves Earth. It might change where it's at, whether it's in your body or underground or up in the clouds or on plants, in plants, in other animals. It's still water.
Right.
Doesn't matter. Well, I guess it's waste, not water, really.
For what?
Pee.
You're taking in the necessary parts of the water, and then your waste is urine that your body doesn't need at the time. still water in a form, but other things too.
Yeah.
That your body doesn't need at the time. It'll just go back into the cycle, the water cycle.
And it'll just filter out.
Right. So the whole water system is a closed thing too. One of the people I used to work with where I work, an environmentalist, he talked about there only being so much water available on the surface of the earth. Think about that. It seems like a renewable resource. It's not, because we are involved in the gas industry. So they take water from creeks or rainfall or what have you and shoot it into the ground to crack rocks. That's fracking, to release the compressed natural gas that's hundreds of feet below the ground. That water isn't coming back for a long time. That water is now trapped under the ground in those rocks. And those rocks aren't so porous that it can seep back out into groundwater and then go back in its system. That's a troubling thought for the whole industry. And that water is not coming back into the water cycle anytime soon. Thousands of gallons of water shooting into the earth, and it just stays there. Because it's so far down and it's so far away from to come out behind rocks, behind clay, behind stuff that's not so porous. It's not just dirt and sand or gravel. It's kind of a troubling thought if you start going down that path. Where were we? While internal human activities do not alter Earth's mass, the planet's mass is not entirely static. It undergoes continuous, albeit minuscule, changes due to natural, extraterrestrial, and internal geophysical processes. Earth is a dynamically evolving system, constantly exchanging matter and energy with its surrounding space.
Earth continuously accumulates mass from space. This gain primarily comes in the form of cosmic dust, micrometeorites, and larger meteoroids that are captured by the planet's gravitational pull and fall to its surface. These infalling materials are remnants from the formation of the solar system, becoming integrated into our planet's matter.
Estimates for the amount of extraterrestrial material Earth gains annually vary, but generally fall within the range of 30,000 to 100,000 tons per year. Seems like a lot. While these figures may seem substantial in human terms, they represent a tiny fraction compared to Earth's total mass, approximately 5.97 times 10 to the 24th kilogram, 6 ronnagrams, for rounding up. Consequently, this continuous accretion of space dust and meteorites does not significantly impact Earth's overall size or its gravitational field in any perceptible way.
Counterbalancing the mass gains are several mechanisms that lead to a subtle loss of Earth's mass. The primary mechanism for mass loss is the atmospheric escape of light gases into outer space. Hydrogen and helium, being the lightest elements, have sufficient thermal energy in the upper atmosphere to reach escape velocity and overcome Earth's gravitational pull, particularly when heated by solar radiation. Earth is currently losing approximately 95,000 tons of hydrogen per year, equivalent to about 3 kilograms
per second,
and around 1,600 tons of helium per year through various escape mechanisms, including charge exchange. Genes escape, and polar wind. Genes.
Keep going, it's in there.
Genes named after British astronomers.
No, you missed the part.
Oh. Gene's escape is not your pants getting up and running into space. Gene's escape was named after British astronomer Sir James Jeans. It means gas molecules get so heated by the sun in the upper atmosphere and are moving so fast they literally leave the Earth's atmosphere. This continuous leakage of atmospheric
Constituents.
constituents is quantitatively the most significant factor contributing to Earth's overall mass loss, when often outweighing the mass gained from incoming extraterrestrial material.
Another, much smaller, contributor to mass loss is radioactive decay. Radioactive isotopes present within Earth's crust and core undergo nuclear decay processes, during which a minuscule amount of mass is converted directly into energy, as described by Einstein's famous equation E equals mc squared. This process accounts for an estimated loss of approximately 15 tons of mass per year. Similarly, as Earth's core gradually cools over geological timescales, it loses internal thermal energy. According to the principle of mass energy equivalence, this energy loss also corresponds to a minuscule decrease in the planet's mass, estimated at around 16 tons per year.
Einstein's theory of special relativity, encapsulated in the iconic equation E equals mc squared, reveals a profound relationship. Mass and energy are not distinct entities, right?
Yeah, entities,
but are fundamentally interchangeable and equivalent forms of the same thing. This means that any change in a system's total energy, capital E, corresponds to a proportional change in its mass, lowercase m, scaled by the speed of light squared, lowercase c squared. If energy is added to a system, its mass increases. If energy is removed, its mass decreases.
The principle has subtle implications for Earth's mass. For instance, an increase in an object's thermal energy, i.e. its temperature, results in a minuscule increase in its mass. While Earth's global temperature fluctuates, a sustained increase could theoretically contribute a small amount to its mass, estimated at around 160 tons per year. This effect is quantitatively very minor compared to other mass change mechanisms. A more substantial, albeit static, contribution to Earth's total mass comes from its rotational energy. A spinning object possesses greater mass than when it is not spinning, with this increase being precisely equivalent to the mass of its rotational kinetic energy. The Earth's immense rotational energy, exceeding 10 to the 24th joules, translates to over 10 to the 7th kilograms of mass. While this is a fixed component of Earth's current mass, any long-term slowing of Earth's rotation would correspond to a slight, imperceptible decrease in its total mass.
The application of E equals mc squared provides a deeper physical understanding of how even subtle changes in Earth's internal energy, such as thermal fluctuations or the kinetic energy associated with its rotation, contribute to its overall mass. This illustrates that mass is not solely a measure of constituent particles, but is inextricably linked to the system's total energy state, expanding our comprehension beyond simple matter transfer.
Synthesizing the various mechanisms of mass gain and loss reveals the overall net change in Earth's mass annually. By summing the estimated contributions, total annual mass gains approximately 30,000 to 100,000 tons, primarily from cosmic dust and meteorites, with a minor additional contribution from thermal energy changes. Total annual mass losses, approximately 96,631 tons, approximately, we get down to the single digit, dominated by atmospheric escape of hydrogen and helium, with minor contributions from radioactive decay and core cooling. Based on these figures, the current scientific consensus indicates that Earth is experiencing a slight net annual mass loss. The most commonly cited estimate for this net loss is approximately 50,000 tons per year. This means that the continuous escape of light atmospheric gases, primarily hydrogen and helium, quantitatively outweighs the mass gained from incoming extraterrestrial material.
It is important to acknowledge that these figures are estimates and are subject to ongoing refinement. The exact net change can vary depending on the precise rates of cosmic dust accretion and atmospheric escape, which are still areas of active research. For instance, some analyses suggest that if the rate of meteor accretion were at the higher end of current estimates, Earth could potentially be gaining a very slight amount of mass each year, rather than losing it. This variability highlights that the precise determination of Earth's net mass changes an ongoing scientific endeavor, reflecting the complexities of quantifying various geophysical and astrophysical processes and underscoring the dynamic nature of scientific knowledge itself.
The heaviness of Earth is scientifically defined by its mass, a fundamental intrinsic property estimated at approximately 5.9722 times 10 to the 24th kilogram. We have said this many times. Let's round that up to 6 ronnagrams. This colossal figure is not determined by direct weighing, but through meticulous calculations rooted in Newton's law of universal gravitation, building upon the pioneering and experimental work of Henry Cavendish in accurately determining the gravitational constant.
Crucially, human activities, including population growth and the creation of man-made objects, do not increase Earth's mass. This is due to the fundamental law of conservation of mass, which dictates that matter is neither created nor destroyed within Earth's system, only rearranged or transformed.
However, Earth's mass is not static. It is dynamically evolving quantity, subject to continuous, albeit minuscule changes from natural, extraterrestrial, and internal geophysical processes. The planet experiences subtle mass gains from the constant influx of cosmic dust and meteorites. These gains are, however, typically outweighed by mass losses, primarily from the continuous atmospheric escape of light gases, like hydrogen and helium, into space, as well as minor contributions from radioactive decay and the cooling of Earth's core. The current scientific consensus indicates that Earth is experiencing a slight net annual mass loss, estimated to be in the tens of thousands of tons per year.
Understanding Earth's mass and its subtle long-term changes requires a multidisciplinary approach, integrating principles from physics, astrophysics, and geophysics. These imperceptible daily changes are nonetheless crucial for comprehending the long-term evolution of our planet and its atmosphere, painting a picture of Earth as a complex, interconnected system in a perpetual state of subtle transformation.
I love it. The whole thing. We asked how much does the Earth weigh, and how do we know? And it's not a simple answer. Any question we have asked does not come out to be a simple answer. It goes so much deeper. Every time.
We can make a simple answer, like
how much does the Earth weigh? 6 ronnagrams. Yay.
What weighs more,
light or shadow? The heck does that mean?
What weighs more, light or shadow? Light. How do you know that?
Thanks, I guess.
Well, how do you know that?
And then as we do more episodes, we seem to just get more comfortable with going on these slight tangents, but somehow doing whatever we're doing brings us to those tangents. Like, who knew? Asking how much does the Earth weigh would give us a whole conversation about ghost energy.
Yeah.
Love it. It's great.
just how conversations work. They can just evolve so quickly.
Yes, exactly. But I just have the deeper questions about consciousness. If consciousness is an energy and Earth is a closed system, and there's 8 billion people, where is the conscious energy coming from?
We get more questions than answers.
Almost every time.
We get about 1 to 3 answers, but at least 20 more questions.
I love it. Question brought.
Question answered. Not even a full hour this time. Only 50-something minutes.
Yeah, that's enough.
Yeah, it is enough.
A production of Wayward Things Network.